Hello everyone, I'm going to talk about the flood emulator in this project. And a flood emulator is developed to implement the real-time flood forecasting. So next, let me introduce this component briefly. The main task of a flood emulator is to act as a surrogate for high PMs to carry out real-time flood forecasting. And in the workflow, the flood emulator works between the rainfall model and the high PMs. And the flood emulator reads the rainfall forecast from a rainfall model, and then to generate the flood depth forecast. So given the forecast, to trigger the high PMs to run and make a double check of forecast of flood depth. The motivation to develop a flood emulator is the high PMs sometimes suffers from large computational expense, especially when it requires a number of simulator runs. In contrast, a flood emulator generally focuses on statistical relationship between input and output, instead of simulating physical processes. So it can alleviate computational burden to some extent. So we can take a flood emulator as a fast and efficient surrogate for high PMs. In this flood emulator, what we aim to forecast is the maximal flood depth for 6 hours at 34 locations. And these locations are spread across Newcastle city center. And these locations may have bigger chance of flooding. The forecast of outputs requires inputs. And here, the inputs comprise the rainfall forecast for 6 hours with a 10-meter interval at a 10 by 10 grid. And these grid cells cover the Newcastle city center. To develop a flood emulator, we utilize a Gaussian process modeling approach. A Gaussian process can not only generate forecast, but also quantify the uncertainty of forecast. So it's useful to measure forecast credibility. Meanwhile, in flood forecasting, we are very likely to run into high dimensionality in inputs and outputs. And such a high dimensionality would pose a challenge to the efficiency of flood emulator. So it's necessary to reduce the dimension of inputs and outputs. And here we adopt the principal components and the orthogonal maximum covariance patterns to conduct dimension reduction. So our emulation strategy is, given the data sets of outputs and inputs, we first use the PCs and OMCPs methods to reduce their dimensionality, respectively. And then we utilize the lower dimensional flood depth and rainfall to train the Gaussian process emulator and learn the parameters in this emulator. Next, based on the trained flood emulator, given each new rainfall forecast, we could generate the corresponding flood depth forecast. So that is to conduct the online flood forecasting. Here, we make a simple comparison of time expense to forecast flooding for 100 rainfall events. So from the table, we can see the high PMs takes about 1 day to simulate 100 rainfall events, while the flood emulator takes about 2 minutes to finish it. So that signifies the flood emulator could speed up the forecast a lot, and it runs faster than high PMs. At last, we use an example to show the forecast performance of our flood emulator. In left panel, the figure visualizes the forecast of flood depth on the map, and the dots mark 34 locations in Newcastle city center. And the color of dots corresponds to the forecast of the maximum flood depth for 6 hours. In right panel, it presents the box plots of forecasts at 34 locations. and the red crosses represent the actual observations. The box plots could reflect the uncertainty of forecast. And we can see about half of the actual observations fall in the boxes. So that is to say, half of them are following 50% predictive intervals. So that indicates our flood-emulator could provide sensible ranges to reflect the actual observation. And it can generate good quantification of uncertainty. So that's all. Thanks for listening.